We've gone through examples on horizontal circle, so I need to go through examples on vertical circle for you. Analysis for vertical circle is a bit different, or some people say it's actually a bit more difficult. Okay, I leave you to judge for that. Right, so earlier we did motion in a horizontal circle. Now we go through motion in a vertical circle. All right, now for motion in a vertical circle, let's consider a mass tied to a string, just like we did on the case for horizontal circle. Now, when you have a mass tied on a string and you try to swing it in a vertical circle, real life example or real life experience will tell you that you tend to need to swing it at a certain minimum speed in order for the mass that you've tied to be able to complete a complete circle. You notice that if, say, you tie a mass and then you try to swing it, if you don't swing it fast enough, the thing will just go up, and then after that, you just fall back down like this, right? But then if you swing it fast enough, the thing will just go in a complete circle like this, all right? So there's a minimum speed that you need to have for the mass in order for it to be able to complete a circle, all right? Anything less than the minimum speed, at most, you just go like this. Then after that, you cannot go to the top, you just fall back down. Right, so you need to have a certain minimum speed in order for it to complete one circle. All right, now when you're talking about something that moves in a vertical circle, by default the speeds will not be the same as they're moving. It's actually due to conservation of energy, which I will show later. But for now, what I'll tell you is that the speeds at the top and bottom of the vertical circle will not be the same, where the speed at the top is usually lower while the speed at the bottom is usually higher. Okay, it's due to conservation of energy. So why do I say this? You can just think of it this way. If I move from the bottom to top, let's look at motion in this direction. If I move from bottom to top, you consider conservation of energy here, you consider the energy changes that occur here. My GPE ought to increase when I move from bottom to top because height increase, right? The mass move from the bottom position to top position, the height is increasing, so the GPE therefore must increase. But according to conservation of energy, if some form of energy increases, some form of another form of energy must be decreasing. So in our case, it must be our KE. All right. Our GPE increase, our KE drops. So when our KE drops, our speed drops. So here, when your object moves from bottom to top, it actually slows down. So that's why I can say that the speed at the top is actually the lowest. It will be slower at the top compared to the bottom. Now, if you were to do the analysis the other way around, you actually come back to the same conclusion too. Where if I move from top to bottom, my GPE will actually drop, but my KE will actually increase. Okay, GPE drop because height is dropping. KE increase now would mean that my speed is increasing. So this one I will actually be speeding up. So same thing, velocity at the bottom must be larger than the velocity at the top. Okay, so I actually explained it here already. As mass moves up, it gains GPE while losing kinetic energy and vice versa when moving down. Okay, now just now I mentioned that you swing the mass, you must have a certain minimum speed in order for you to complete a circle. But say you swing it too fast, you overdo it, you can imagine that it will eventually snap. Okay, if you swing it too fast, overdoing it, the string will eventually snap. But where it snaps will always be the same. It will always be snapping at the same position. So what we'll tell you is that you swing the object faster and faster, the string will usually snap at the bottom because the tension at the bottom of the string is usually the larger one. It's usually the larger step. This one I will show you in the analysis in the box below. Okay, so these are some things to note first. All right, speed being different, tension being different for something that is moving in a circle. Not to mention, you also need to have a certain minimum speed. Okay, so let's look at the analysis here. Okay, so if you look at the diagram on the right, it's actually the object moving in a circle, but this one with the forces indicated. Now, for our analysis, I only want to consider the bottom and top position. The bottom and top position is where you have values at the extreme end. Anything in between, let's just say here and here, will just be in between the extreme ends, okay? That's why I don't consider any other position other than top and bottom. It's because the top and bottom is where the extreme values are, all right? So let's consider the case where the object is moving and what are the forces. Now, at the top of the circle, where my mass is, I would have my weight mg acting downwards. I would have my tension acting on the mass downward. Okay, this is talking about the forces acting on the mass. I'm not talking about forces acting on the string. I'm talking about forces acting on the mass. For the mass itself, weight will be downwards, tension by the string will be downwards. Okay, at the bottom of the circle, my weight will again still be downwards, but my tension by the string will be upwards. Okay, so these are the forces acting on the masses right now. If I try to analyze the forces at the top of the circle and the bottom of the circle right now, you consider that this thing is moving in a circle, therefore you must have centripetal force. And I know that centripetal force is provided by some existing force. Let's look at the top position first. Top position, I know that my centripetal force is directed towards the center of the circle, so it's downwards. Mg and tension are in the same direction as my acceleration, so this one is considered to be positive. My Fc would actually be equal to mg plus t. Okay, then Fc by itself would be equals to mv top square divided by r equals to mg plus t. Okay, wait, maybe I redo this. I write this properly for you. I write it the other way around now, just so it's easier to see. Okay, so the centripetal force at the top will be mv top square divided by r. Fc here will be tt plus mg equals to mv top square over r. This is the expression that you are having over here. Okay, so what I'm really interested in knowing is what is the expression for the tension. The expression for the tension is this: tt is mv top squared over r minus mg. All right. Then after that, you look at the bottom. This is analyzing the bottom right now. Centripetal force is mv bottom squared divided by r. Now here, my centripetal force again is directed towards the center of the circle, but this one is now upwards now. So I look at the forces that are acting. TB, tension at the bottom, same direction as acceleration, will be positive. Mg opposite to my acceleration, it will be negative. So here I would say that TB minus mg is equals to mv bottom square over r. So that TB is mv bottom square over r plus mg. Okay. Now, if you try to look at the tensions right now at the top and bottom, tension at the top is mv square over r minus with mg, but tension at the bottom is mv square over r plus with mg. The first one is minus off the weight. The second one is plus the weight. So if you try to do a comparison right now, obviously TB will be more than TT. Tension at the bottom will be more than the tension at the top. That's the reason why here we say that your object will actually always snap. Sorry, your string will always snap at the bottom first. It's because your tension there is the largest. It will actually reach your breaking force first there. Okay? That's why it snaps at the bottom. So this is looking at the tension. Okay, now just now I mentioned earlier also that there's a certain minimum speed with which your mass need to move so that you're able to move in a circle, right? So what are the speeds that we need? How do we find out the minimum speed required? This one will be the analysis at the bottom here. Further at the bottom here, let me just get back some of those stuff. Okay, so if you look at the analysis again, for the case where something moves from bottom, sorry, different color. For the case for mass that moves from bottom all the way to the top, now if it's not able to complete a circle at the top, if it's not able to complete a circle moving like this, what we can say here is this. At the point where the mass is not able to complete the circle, at the point where the mass is not able to complete the circle, tension is 0. So maybe I do it the other way around. At the point where the mass is not able to complete the circle, the string will start to slack. Okay, the string will start to slack. Therefore, tension is 0. Okay, so you consider the case where something is at the point of not being able to complete the circle. All right, so when the thing moves up and is at the point of not being able to complete the circle, the string will actually start to slack. So when the string starts to slack, tension will be 0. Okay, so we consider that case and apply to our analysis. String starts to slack when Tt is 0. So this equation that we have, we replace tension as 0. We get 0 equals to mv top square minus over r minus mg, such that the velocity at the top is square root gr. This is actually the minimum speed required at the top so that our object is able to complete the circle. Anything less than that, it won't be able to complete a circle. Anything more, it will be able to complete the circle. Okay, so this is the velocity at the top, minimum velocity at the top. But how about the minimum velocity at the bottom? Just like I mentioned to you, the velocity top and bottom will not be the same, right? So velocity at the bottom will be different. So how do we find the velocity? This one you have to consider conservation of energy. Okay, by considering conservation of energy. So if we consider conservation of energy, when the thing is able to move in a circle, and then it moves all the way down, when it moves from top position to bottom position, the height decreases, so GP drops, and then subsequently KE increase due to conservation of energy. So if you apply conservation of energy here, loss in KE equals to gain in GPE. Our loss in KE is actually half mv bottom square minus half mv top square equals to mg2r. All right. Now, one of the things I would have probably mentioned to you guys before was this. For changes in energy, always take higher value minus the lower value. Okay, changes in energy, when you want to use energy change equation, always just take higher minus lower. Okay, don't need to be bothered about whether should it be the final minus initial or initial minus final. Just take whichever is larger minus of the lower one. Okay, so always take the higher value energy minus of the lower value. So here, how do I know which one is higher, which one is lower? So just now I mentioned to you, GPE drops, KE increase, velocity at the bottom will be more than the velocity at the top. This in turn tells you KE at the bottom will be more than the KE at the top. So KA at the bottom will always be larger than the one at the top. The bottom KA is the larger value. That's why I would take half MV bottom square, half MV bottom square minus half MV top square. All right. And then other than my change in GP is my delta H, right? Mg delta H. My delta H is this one, which still happens to be 2R. Okay. So you get that equation. Then after that, you want to sub in something else again. You want to get rid of the V top here. Okay. Now you already found out V top is actually square root GR. If you square it, V top square is actually GR. That's why this one can be changed to GR. All right. So you sub it in, you rearrange it, you get this, you simplify it, you will get V bottom equals to square root 5GR. So this is the minimum speed at the bottom required for your object to move in a circle. Anything less, it won't be able to move in a circle. Anything more than that, it will be able to move in a circle. Okay, so this is the analysis for vertical circle. All right. Now the analysis for the vertical circle, like this one, all this while it never came out before. From 2004, from 2002 until recently, it never came out at all. It only came out around November 2021. Okay, so previously it wasn't really that important to know, but somehow in the last two exams, in the more recent exam sitting, this actually came out. So I won't say this one can be neglected anymore. It's something that you still need to know. The derivation looks a bit complicated, but you look at it a few more times, you probably get used to it. All right. Okay, so let me clear the writings. There's another last example here, also on something that is being swung in a vertical circle. Now, sometimes rather than having a mass tied to a string that is being swung in a vertical circle, this time we have a bucket of water that is swung in a vertical circle. So I'm sure maybe you have tried this before. You go and put water inside a bucket and then you try to swing it in a vertical circle. If you don't swing it fast enough, the water inside the bucket will fall down at the top, right? When your bucket reaches the top position, if it's not fast enough, the water inside the bucket will start to fall down, right? So you need to make sure that you are swinging the bucket fast enough so that the water remains inside the bucket. So here, how do I know what's the speed in which I need to swing the bucket so that water remains inside the bucket, so that the water can complete a circle? The analysis here would be exactly the same as what you did before. The only difference now is the forces that you are considering. You would have to change out one of the forces. So if you consider the case for the water inside the bucket, at the bottom position, if you're talking about the forces on the water itself, you still have the weight mg, and rather than having tension acting on the water, you now have reaction force instead. Okay, it is no longer tension, it is now water, the reaction force. The water is liquid, right? You cannot actually tie a string onto water and then say that there's tension acting on the water, right? So no, for the water right now, there's no tension. Okay, before this, there's tension acting on the mass, but this time water is liquid. You don't have such a thing called tension. All right, what you have instead is reaction force. So at the bottom position, this one is easily understood. Your water is resting on the bottom of the bucket. It pushes down on the bucket, so the bucket will exert a reaction force upwards back onto the bucket. Okay, so these are the forces that you have. Now, when you go upwards over here, you still have your mass, you still have your weight acting downwards, and you also still have your reaction force. But this time your reaction force is downwards. Okay, now the reason is because of this. You see, because of, you know that in Newton's first law tells you that any object that moves will have a tendency to continue in its state of motion, or whether it will continue to move in a straight line. So that one is what we call inertia. All right. If we have the water that is being swung in a vertical circle like this, at this top position here, your water has a tendency to want to keep moving forward. All right. So it has a tendency to keep moving forward, but then your bucket is actually preventing it from moving forward. So what will happen is that the water actually pushes onto your bucket. So the bucket in turn pushes back onto your water. So as a result of that, you're going to have a reaction force downwards. Okay. So your reaction force here is downwards, not upwards. Okay. It is downwards because your water tries to move out of the circle. As a result of it trying to move out of the circle, is pushing against the bucket. So in return, the bucket pushes back down on it. Okay. So that is the origin of the reaction force downwards. Now, when you look at the forces right now, it's actually the same as what we have in the previous diagram. Just that rather than having tension, is reaction force right now. Okay. So the analysis that you do is exactly the same. Okay. Eventually, you come to the conclusion that the velocity at the top must be square root GR. The velocity at the bottom must be square root phi GR. Okay. The analysis is exactly the same. Okay. Right. Just make sure you know how to identify the forces and the direction, and you should be fine from there. Okay. So with this, we're done with the concept part of circular motion.